Okay, so we will not wait because we only have 4 classes left. Okay, so once it's at 2:30, we'll begin. So today we will just go through the DNS first because we have a quiz for DNS, and that will be the last quiz. Okay, and after we release the quiz, you will have 1 week to complete. Right, so we will make it a little bit longer than 1 week. Okay, but anyway, so it's better to complete it before the exam, right? So, and after that, we will go back to our previous lecture, which we left behind last time. Okay, on Monday. All right, so let's begin because I think only 35 students right now. Most students will be coming, so we have to begin. Okay. Yes, this lecture is about DNS, domain name system. So, why we need it, right? So, for example, if you want to call somebody, you need to ask for their phone number, right? So, you cannot just say, "Hey, give somebody's name," and you can call somebody, right? And so, if you want to email somebody, you need their email address first, right? So, in the internet, right? So it's the same. You need to know the IP address of the destination. For example, Google. Right? But do you even know Google's IP? I think the answer is no. Right? So we need some domain names that are easier to remember than IP address. Right? IP addresses are just 4 numbers, right? So which is very difficult to remember, and we need a human readable names, which are the domain names. Okay. So here are the internet names and the addresses. Okay, so the addresses are IP address you see earlier, right? And these are used by computers to give unique destination for each machine, right? And it really conforms to the structure of the network, especially the prefix, right? The prefix is in higher level in a hierarchy, usually for a region. Right? So, and you also have names, right? So like a UA or UAB.edu. Right? So you know that this is for University of Alabama or University of Alabama Birmingham. Okay. So these are used by human. Right? Human can remember these addresses, and and we will see later. Okay, so the domain name. Okay, actually you read from right to left. Okay, edu is the first level, top level, so called the top level domain, TLD. Then UA, for example, here is the second level. Okay, and www means it's a web service. Right? You can also have a mail or something else. Okay, and you can even, let's say, you can have somebody's name. Right? But that's fine. It's not. This is not the highest hierarchy. This is the lowest in the hierarchy. Okay. So how we'll see more in details later. Okay. So how do you map, let's say, domain name to the IP address and IP address to domain name? Usually it's a domain name to IP address because when you visit, you want to use a domain name, but get IP address so that you can put in the IP, datagram to deliver to the destination by the routers. Okay. So this is by so-called DNS, right? Domain name system. Okay. So there's a history of how the domain name system comes about, right? In the old days, like the ARPANET, people just put everything and the etc host. This is still the case for now, right? So if you have let's say in your department, like in our department, you have different server names, okay? And usually each machine will have a copy of the host, okay? Host file and the etc host, right? And there you will have, hey, this IP address is this host name, that IP address is that host name. So you can just visit using that host name, okay? And in Windows, you have another location to keep that. Usually servers are using Linux. So this is actually a bad choice before DNS, right? So it's a centralized system and manually changed, right? So previously it's maintained by Stanford Research Institute, SRI, okay? And you need to change, if you have a change in the mapping of your domain name to the IP address, you need to email to SRI. Okay? And the machines will periodically FTP new copies of hosts down to the local machine, right? Because SRI has the most authoritative copy of the host. And you periodically pull this back because there will be update by emails, okay? So administrators will pick names that they like, okay? Right, so some name can be something like this, right? So basically any name is allowed. But But then there's a transition toward the domain name system, DNS. The reason is that having SRI, one institute maintains all the mappings in a host.txt file, and the etc host is not scalable, right? So it's hard to enforce uniqueness of names, right? So if two different institutions both want to use, let's say, MIT, right? So you need to say, hey, there's a one for MIT already, right? Marble Institute of Technology, you cannot use that. Right? So maybe Marble Tech or something, right? So you need to differentiate that, right? So, but if it's a plain text file, it's very difficult to guarantee that. Right? And so another thing is that many machines have inaccurate copies of hosts, right? Because if you don't synchronize with SRI timely, then if there's update on the mapping, so you will not get the latest mapping, and you will go to wrong place using the domain. Okay. So this is the reason why DNS comes about. Okay. And again, DNS at the very high level is domain name system. Okay. And you can regard it as like a distributed database, right? Because it's a key value store basically in some sense. But it saves more than just key values. We'll see later. Okay. But at the very basic, it's a domain name and an IP address. Okay, a tuple of domain name and IP address. There's no centralization. We have a lot of domain name servers. We'll see later in the next slide. Okay, collectively store this database. And it's adopting a client-server architecture where the server. So previously, SRI stands for Stanford Research Institute. It's the only server. Right now we have many servers. Okay, it's a distributed, but still we have dozens of servers. Okay, and then when you need it, you are client. Right? So it's a client-server architecture, and the communication for the DNS is using UDP port 53. Okay, so this is DNS is you can regard it as an application layer. Okay, on top of UDP, right? So some implementation also use TCP. This is actually another important concept is that the domain name is actually read from right to left, right? So in the hierarchy. Okay, originally it's flat, right? It's like a host name, a huge host name. Okay, host name file. Now it becomes, if you have mail.google.com, you should first have com, and then Google, then mail. Com is the most high level. All companies end with com. Okay, and then you have Google, you have mail. And there are also some other companies in other countries. Maybe they maintain their own, like Netherlands NL, right? So for example, and then they have .com, .nl or something. Right? So usually in US we just have the .com, okay? and with this. In different other countries they have their own, maybe those kind of servers to maintain the domain. Right? So let's take a look at the name hierarchy. Right? So there's one very authoritative root domain, okay, root server. It keeps all the so-called top-level domains, right? So called TLDs, right, at the very top. Right? So you have like .net, .edu, .com, right? Government, military, organization, org, etc. And for different countries, UK, France, and they can then have their own companies maintaining these, right? .com, .uk. Right? And then in the edu, for example, we have uab.edu. This is the second level. Right? UAB has a server, right? It's an authoritative domain name server, okay? For everything under UAB. Right? For web page, it's www. Right? For email, it's email.uab. Right? So BlazorNet, right? You can have different third level, okay? So how many of this level you can go all the way to, right? So there's a restriction that the maximum tree depth can be 128. But I don't think anyone will use something for 128. Right? That's great. Okay, but keep in mind, so TLD, right? When we talk about top level domain, okay, these are the top level domain. Okay, TLD, and so this also avoids name collisions, right? So for example, if you have uab.edu, you have another company named UAB, right? So for some other company, right? So then there's no conflict. So this is again read from right to left. Okay. This is the top level, TLD. Okay. So the administration now it's no longer by one institute, right? SRI. Now it's by different service. For example, so each actually the tree is divided into zones. Right? We call zone, for example, UK has their own zone. Right? So France has their own zone. Right? So US have these, right? and actually UK maybe has another level of this. Okay, so each zone has an administrator, right? So basically, they are a company or organization running some of the domains. Okay, and responsible for part of the hierarchy, right? They collectively maintain the whole domain name system, but each one does not maintain everything. Okay, this makes it more scalable. For example, for the root, right? So the root basically maintain, hey, for edu, for net, for org, for UK, who you should contact, right? So that top level TLD mapping is maintained by root, right? It's maintained totally by the ICANN. Okay, we see that earlier. And then VeriSign is maintaining those net, edu, com, governance. These are very commonly used, so it's maintained by this institute, right? And then if you are like in UAB, we maintain everything within UAB, right? So it's something like this kind of organization. So you can see this is more scalable. So this is what we call the server hierarchy, right? So there's a DNS servers together functioning as the big distributed database, right? So that's for each DNS server, okay, the authority is only over a portion of the hierarchy, right? So there's a subtree, and not even a subtree, right? So for example, if you are EDU, you don't get into the UAB details, okay? Everything, so you are only look at this one level triangle, in some sense, right? So one level triangle, okay? And within this, you can let the lower level server translation. Okay, so this is way more scalable. No need to store all the domain names. Okay, DNS in one machine. Okay, and store all the so it will store all the record for host and domain in its zone. Right? So basically, this is what we call you have your authority of everything within your zone. For example, for UAB, then everything like mail, www should be stored with UAB. Right? But every institute registered with the EDU, right? Every university registered with EDU, they should have, the EDU server should know whom to contact, right? To the respective university server, right? And this may be replicated for robustness. Okay, so maybe for some big companies like Google, right? So you want to DNS server have multiple of them. Like if one is down, someone else can still access. And so everyone knows the root server, okay? The address of the root server. Because if you don't really know, let's say I want to go to some .gov, right? I don't know where to find. You can contact root server. Root server will tell you, hey, contact here, right? You can go level up. So the root server should be known by everyone, okay? Because you will have other names what you contact upper level. And the root servers know about all the TLDs, so all the top level domains. Okay. So here, let's take a look at the root name servers. Actually, we have a bunch of them. So it's not just one of them. So this is important for robustness. Okay. So it's administered by ICANN, and there are 13 root servers from A to N. Okay. And the 6 are anycasted. Right? So what it means is that these 6 may be super important, right? It's globally replicated. Let's say this is, let's say you have the same domain name content, maybe in China, in US, maybe in Europe. There are different replicates. If you are here, you will go to your closest domain name server to get the address of it. Okay. If you are in Europe, you will go to here. Okay. So this is called anycast. You have a group that replicates the same data, but you will just go to the closest one to communicate. This is different from like there's a multicast, right? You need to reach everyone. Right? Anycast means you just reach someone, right? Because they all have the same content. You just go to the closest one. They are globally replicated. If one server is down, then you will go maybe to the second closest. Okay. And they are only contact one names cannot be reserved. Right? So for example, you already catch this information. You know where Google is, right? So you don't go there. For example, in UAB, right, a lot of people use Google for sure, but then UAB's authoritative server should already know where the Google server is. You will not frequently contact EDU server. So here's the map of the routes at the top level. And you can see they are split into many servers. But again, it's a specified service. Right? This list is maintained by ICANN, so that when you really don't know how to where to go to, right, so you contact them. But try to contact them less. Right? That's why we need a caching. Otherwise, everyone in the world will be contacted. So you also have so-called a local name service. Right? So this is each, for example, if you are in your home network, you connect to an internet service provider, right? They have a local default name server for you. Okay? When you want to visit Google, right? You actually go to their DNS server, right? Local name server, okay? And then they return you the IP address. Okay? And this is often configured by DHCP. DHCP is a protocol that dynamically assign IP addresses. Okay. If you have interest, you can look into that. So if you think about how you get to, let's say you go to a classroom, you connect to UAB Wi-Fi, right? Like it's secure, or UAB secure, then it's using DHCP to assign you dynamic IP address. Next time you connect again, it may be a different IP address. Okay. So the IP address pool. And the host will then begin DNS queries by contacting only the local name server, right? So this is the first hop you contact. Okay? And because so many people, let's say at UAB are using this server, then it will frequently cache query bots, right? Whenever it cannot find something, it will contact the up level. But then these records are up to date, right? It can keep them and for other people to use. Right? You don't need to contact an EDU again, right? Or come again. So here's the example. What's google.com? Right? You go to Google com server and get it. Right? After that, it will cache, and the other people will not need to do this additional access again. So there's a concept called authoritative name server. Right? So authoritative name server is saying that it stores the name and the IP mapping for a given host. Right? So for example, you think about this root is UAB or EDU. Right? Of course, your let's say your web page, who has the authority to say where the server location for the web page of UAB? Of course, it's a UAB's DNS server, right? It's not a MIT's DNS server, right? So this is called an authoritative name server. Okay, you must have a particular machine that is responsible for that. I think this is pretty easy to understand. So this is authority for anything and the UAB.edu. This is anything and the edu. Right? If you want to visit, let's say, MIT.edu, you will not go to .com. Right? So these are you know the authority of each server, so you know whom to contact when you need the information. Okay. So for example, here where the UAB.edu, you will go to edu server, right? And then you will go to UAB.edu server. Right? And then this caches this location for www, then it will get back. And then those requested IP address can use it, okay? Or can cache it, at least. So every host knows a local DNS server. Right? So whenever you send some request, the first hop of the DNS server that you send request to is a local DNS server, okay? But if the local DNS server can also the query you are done. Right? So for example, it's an authoritative server, right? So you are visiting another page at UAB, and you are right now at UAB, right? And that's that, okay? Because they don't need to ask somebody else. Right? Or your local server is not like if you are contacting Google.com, but UAB's DNS server is not an authoritative server for UAB, not for Google, right? But because other people visited that, right? It's cached. You know where the Google server IP address is, then you can reuse it. Okay, it's called a cache. Otherwise, if both don't know, right? So let's say somebody visits a very rare web page where no one ever visited, there's no cache there, right? So then, or there's another possibility, right? So there will be a timeout, okay? We'll see that later. And so it will go down the hierarchy and search for the authoritative name server, okay? Right? So we have a tree hierarchy, it will search, right? So keep in mind that every local DNS server knows the root service. So it can directly, if you go to like Google.com, it can contact com immediately, right? And so it can also use cache to skip steps if possible. So it can skip the root, directly go to com, if it knows where the com is. So there are two ways to do this kind of query, right? So, but this recursive DNS query is one way that is not actually adopted. So let's take a look at the concept, right? Let's say you want to visit Google, but you are right now at UAB. You will contact your UAB domain name server, like old Indo CSD, right? At a CS department, right? Then it doesn't know where, let's say there's no cache of Google.com, right? So then it will contact root, right? And assume you already know the root, of course, you will directly go to com. Okay? Now root say, hey, contact the com, right? So instead of you contact com, root will it's a recursive, right? So you're here, you contact this server will then contact root, right? This root will then contact com. This com will contact the Google.com, right? And the Google.com know where the server IP address is. And then we'll go back. This is called a recursive. Okay. But you can see during this process, right? This thing has to be hold until you get back to here. Right? And this thing has to be hold until you get back to here. Okay. So there's a lot of status maintenance. So this is actually why this solution is not actually adopted. Okay. And once it get back to you, right? Then you can directly communicate because you know the IP address. It puts a burden on the contact name server. Whoever the contact, it has to maintain the status until the message comes back. Okay, and this is not good, right? So it will maintain your request ID, so it knows which one is which one, right? And it will respond to you correctly. But this kind of information maintenance is like keeping state, and we know that the internet we want a stateless, just like the routers, right? So you don't care about, you don't want to hold a connection until somebody else handled and then get back. Okay, that's a lot of burden, honestly. So the actual solution used is called iterative DNS query. Okay, so what happens is this, right? So you will always go to your local name server, right? And then the local name server tell you, hey, I don't know, where's Google, okay? But I know who you can resolve to, right? So like you can ask a root for com, and then com will tell you where the Google.com, okay? Then it will get to Google, right, and tell you. Okay, so now you should. Oh, actually, this is not by you, by the local name server. Okay. So this local name server will hold the status, but not everyone else, not on root and on com. Okay, it will contact root and then get com. Right? It's like, hey, I don't know what's Google, but I know who is com. Okay, and then you go to com. Right. So this time root will just respond to you with the com. Okay, com will just respond to you with the Google.com. Right? Then it's done. There's no status maintenance. Okay? And then you contact Google, and then you come back. Once at this time, Google tells you what the IP address, and you forward it back. Okay. So this is iterative because this is 1 iteration, 2 iterations, 3 iterations. Okay. This is actually how DNS works today. So a lot of burden on your service provider's name server. So that's why you are paying. Okay? They should do the job. And so another thing is a DNS propagation, right? So let's say you purchase a new domain name and also get a space with some IP address, and you put your data, like web pages, onto that server. Okay, and then you buy a domain name and you say, hey, this domain name, go to this server to visit my page. Right? It can take up to 72 hours, which means 3 days for your name to be accessible. Okay, so this is called the delay of DNS propagation. So for example, once you have a new thing set up, like new site, so what will happen is, so the ideal way is you go all the way to here, right? And then go to the com server, right? Which this is the com server, know where the com server should be, right? And it gives the IP. Right? But this would fail because you think about it, right? So you already cache what is com, because a lot of people are checking what is in com, right? And you already cached that, then you cache all these hierarchies, right? And you will not really contact com again, even though this is new, right? So that's a trouble here, right? So you probably just say, hey, in the com file, there's no my new site. Okay, that's why oftentimes when you have a new site, it takes some time to update. So the zone file can be cached for 1 to 72 hours. What does that mean? So the cached data will not live forever. Right? let's assume it's cached for 1 hour. Right? There's a time to live. Okay. After 1 hour, right? After 1 hour, it has been cached for 1 hour. If you contact again another request, it will think this is no longer valid. It will contact again. So ultimately, after the cached allowed time, it will get the up-to-date information. Right? But there's a significant delay here, right? Up to 3 days. Okay. So from 1 hour to 3 days, right? Depending on who is running the, your service provider. Okay? Because you think about it, if you don't cache a lot, you just make the time really short, right? So then you will basically keep requesting for COM or root, and this is a lot of burden on the up level who is serving the whole world, right? So, and it's also a lot of communication from this server where the service provider need to pay them. Okay, so you can see that at least 1 hour. Right? So if you have a new site within 1 hour, it's probably it will not reach everybody. Okay, in the world. But after 3 days, you are guaranteed it will reach. So here, this is where there's a time to live TTL associated with it. So let's take a look at how the DNS records is looking like, right? So we said it's a database, right? And in the very basic type, it should be the domain name, right? And then you have the IP address. So but actually there's a lot of format, right? So if you configure a domain name and you want an email address, you have an MX record, you need to also configure, right? There's a mail server. Right? Let's take a look at how these things are looking like. Right? So each DNS query will have 2 fields, right? So name and type. Okay. Right. So type is what type of the record is. Right? You have different types of record. We'll see later. Okay. Then you will have a key value pair, which is name and value. Right. Let's take a look at some examples. And there could be multiple records returned for 1 query. Okay. So you have 1 query, but there's a list of records. Let's say you can say, hey, where's the keyword search Google server, right? It has multiple choice for you. Right? You can choose the closest one. It can have multiple records. And what is the name and the value here? Right. So so name and value depends on what's the type of the record. Right. So the most obvious type is A type record. Okay. And you can also, if we are using IPv6 instead of IPv4, it's AAAE. Right. It's 4A types. Okay. And in this is our most regular type of record, right? So the name is domain name, the value is IP address. And you can have multiple IP addresses, okay? Like Google.com, then you have this. So for example, here you can send a query, say, hey, this is domain name, right? I want its IP address, right? So value is IP address. This is the A type query, okay? And because it's A type query, it will return your IP address of this domain name, right? And the second is called NS record, okay? So the NS record, the name is a partial domain, right? So you don't have the entire domain, the higher level, okay? And the value will be the name of the DNS server for this domain, okay? So this is for iterative query we showed earlier. Let's say I want a www.edu name server, right? So it will give you NS record name server. So it will give you the value. Okay, you can send your query to this spot. Okay, so this is really for the iterative. So this IP address is potentially not the www.edu, but where you can get the IP address for www.edu. Okay, A is the exact IP address. Okay, and there's another type called CNAME. CNAME is a host name, right? So the name is host name, and the value is canonical host name. Okay, this is used for alias. So it's because you sometimes you want a different names. Okay, for example, you can have food.mysite.com, and then you can also have actually it will be kind of redirect to bar.mysite.com, right? So a set of different domain names can point to the same IP address. In that case, you will have one domain name as a canonical. Okay, and I'm sure that you probably see that. Right? So maybe people give you a lot of redirect, different URL that can go to the same page. Right? So they will be translated to a canonical URL anyway. Okay. So I think even for our page, right? So if you use cs.uab.edu, right, we'll go to, or you have CIS, it will redirect to CS, right? Because previously the department named the CIS, right? Okay. And you also have the mail, right? MX record, okay? So this is for the mail server, right? So because if you do, by default, it will give you the web server, right? So for the web page. So MX tells you, hey, you should go to the email server. Okay, that's running a different kind of protocol. Web page is running the, HTTP or HTTPS, right? This is running SMTP, different kind of application level protocol. So we don't have time to cover those, but DNS is also application level. Right? So these are the application levels that use TCP and UDP. Okay, but they have additional header. Okay? And here, for example, you ask for the same uab.edu, but it's MX record. It will not return you www. It will return you where the mail.uab you should come. Okay? So there's also a reverse lookup. What is a reverse lookup? Right. So usually you give a domain name, right? Google.com. You want its IP address, then you can you can go there. Okay. But you can also do the reverse. Right? This is there's a separate but similar server hierarchy stores the reverse mapping. Okay. So rooted at these places. Okay. Alpha. Okay. So what they do is actually this is called a PTR, a pointer record. That's a PTR record. Okay. So where you give the IP address, the key is no longer domain name. You give the IP address and it returns you the domain name. So that means if you know the IP address, you can actually even get the domain name. It's pretty interesting. Okay. So for example, here the type is PTR, then you will get the domain name for this IP address. So the domain DNS can be used as a indirection service, right? So it gives very powerful capabilities. Okay, right? It's surely will give human better reference to machines. Right? You don't need to remember the IP address, but you can also have other benefits. For example, you can change the IP of the machine. Right? But for example, now Google decides to add a bunch of new server and retire some old server. Right? So IP address will change. Okay, but you can still visit them because it's still Google.com. Okay, so you just need to change the DNS record in the DNS service. Okay? And people, from end user perspective, you can also have different names. Right? So you can have different names running on the same server. Right? So for example, let's assume that for Square and Reddit, they want to share the same domain name server. Right? So that's good. They will be direct to the same IP address. Okay? And you can also have one domain up to multiple machines. Right? So for example, if we are using Google, right? Surely so many people are using Google for keyword search. Right? And Google is replicating the same service on different IP addresses, then it will return you some list that you can choose from. Right? So we will go to the closest. Right? Okay, so here is an example of content delivery network like Netflix. Right? So if you are here on the west, and then you will contact the Netflix server that's closest to you. Right? And if you are on the east, you will contact another Netflix server. Okay, here's an example. And the DNS records may vary based on your location, okay, and service provider. So these servers will be tuned to even decide, hey, we should just return this part of the IP list of IP address, not that part, right? Because that's closer to lower latency. Okay. So DNS is very important because otherwise you cannot just using domain name to visit the website. Okay. And so you think about it, right? So if you are signed up, right? So even if you want to use some session-based visits, right? So you sign up for some account in somewhere, right? And you will need the email verification these days, right? Then of course you need to access your email, right? So it's like your email should be secured, right? So people trust your email. If you can answer that in your email, then people think it's you. Okay? So this is very important because if your email server is compromised, right, it goes to some malicious server for the email. Right? So then everything you send and your password, etc., will be taken by the malicious user. Okay? So the DNS is the root of the trust for the web. So if you type Bank of America, you want to for sure to go to Bank of America. You don't want your local DNS local name server to bring you to a compromised site. Okay. Okay. So DNS server should be very secure. Okay. And so actually, a DNS server, if some up-level server get attacked, that's not a big trouble actually, right? So, for example, we can have the denial service attack we mentioned earlier, right? So you can keep sending requests to the DNS servers until they can't have too much results and fail. And so then they cannot serve other people's requests for the DNS records. Okay. There actually have been massive distributed DOS attacks against the root name servers. So, but is this having a huge impact? The answer is no. People don't even notice, right? Because those zone files are cached, right, for hours or even up to 3 days everywhere. So these name servers are not frequently visits. Right? So the probability that you visit because the TTL, time out, right, time to live expires, is very low. So most of the time you can still get to the right location. Okay. And the more targeted attacks can be more effective. So if you attack the root server or upper level server, may not be that useful. But you can attack, let's say, UAB's DNS server. Right? If that's the case, everyone in UAB cannot get the IP address, okay? Because that local server is down. Okay. Then you give a domain name, you don't know where the IP address is. Okay. You can also attack the authority server. Let's say you attack, for example, Google server. Right? Then Google is down and you cannot visit Google. There's also like a concept of DNS hijacking. So what it says is that you can infect the operating system of the server with a virus, okay, Trojan, okay, and so these kind of programs, virus, Trojan, will change the entries, okay, in the etc host. So for example, it can change the server's bankofamerica.com to to the some evil, right? So some site that want to steal money. So this is by virus, by Trojan. Okay, this is one method. The second method is called the man in the middle. So, for example, if the attacker can establish a connection with the server and then establish a connection with you by for example, fool you to connect to the like an evil bank in the middle. Okay, and then but this guy doesn't want you to know it's eavesdropped on your message, right? It will forward the message to the right server and come back, okay? But you are not aware. So you have a request, it takes the information but sent to the server. The server responds the normal message, but it's also hijacked by this guy, right? And then sent to you. So you are not aware that you are actually communicating with a bad guy, right? Because the message seems normal, right? Once you click to the evil bank. Okay? This is an example of the response spoofing. You eavesdrop on a request, and then you can respond to the client. Okay. And here's an example. So where's Bank of America? If you go to the normal, authority server, you will get the right address. But what if, let's say, you somehow get the virus, right? It tells you, hey, you should go to here. So then it overrides your, domain name server, to a bad one. Okay? Then it will tell you, hey, go to this malicious site. Okay, and then your bank account, etc., is compromised. So there's another concept called cache poisoning, right? So here you can see that the domain, your local name server is compromised. Here, your local name server is not a malicious one, okay? But you can still compromise. And so, for example, you can visit with Google and right? But then you can get a wrong message here. Right? Say, hey. So you remember when it's time to leave the timeout, you can request this IP address again in case it changes the server location. Right? So then some malicious user can fool the server to say, hey, now the new address should be this address. Now future requests will really, go, you will get the wrong information go there, even though the local name server is not malicious. Okay. So until the TT expires, or next time the TTL of the bad record expires, right? All the queries will be returned, will get this bad address, IP address. Okay? Then everyone is visiting this malicious site. Okay? So this is actually much worse because you can attack a normal server, and then they are telling your service provider is telling you some bad information. Okay. So this, I think this has been quite severe, right? So then people get this solution for the DNS stack to add some security. This the DNS security extension. So the solution is really to digital signature. Right? So cryptographically sign the record, okay, the critical resource record. Okay? And then the resolvers can verify whether it's really signed, right, by the true, like say, whether it's signed by Bank of America. If you cannot sign it, right? People will know who is the public key of the Bank of America, right? And then you cannot sign it to pass the public key verification. Okay? Only the one with the private key can properly sign. Okay? And so this is called the public key system, right? So public key, private key. Right? Using cryptography method, right? If you have a private key, you can sign, but you will announce a public key to others. Other people cannot know your private key, right? And you need the private key to sign. Okay, otherwise no one can sign. But once you sign, people can easily verify using public key. That's a cryptography concept. Okay, and so now there's two new resource types, right? So DNS record. Okay, so one is a key, right? So the domain name and the public key of the zone. So this should be the key that you use to verify the signature. Then you also have a resource record signature, right? And this is the query itself. Right? So, and given the query, the query result will be signed. Okay, so which means we have it's a encrypt with a private key. But you can use the public key that you get to verify it's really signed by that. So this creates a hierarchy of trust and prevents hijacking. It's actually deployed in the root in 2010. Okay, hopefully it's not too late. Right? And by VeriSign, which manages a very important domain, so .com and .net TLDs in 2011, and a lot of other ISPs are supporting that just for security reasons. Okay. So, for example, why this works? Let's take a look at it. Right, so here we want to ask where's the Bank of America? Right? Bank of America will return you because Bank of America has its own signature. Right? It will return you as use a key and assign this message to you. Okay, and then this message to you, you need to see, hey, this thing, is it properly signed? Right? So then you need to go to, because this is BOA dot B of A dot com. Right? So you need to go to .com to say, hey, is this right? Are you signing this? Right? Okay. It will say, hey, yes, I'm signing this. But another possibility is this .com name server is actually malicious, right? It's compromised. Then, this signature itself is already signed up level. Then you need to say, hey, are you really signing this key? Right? So the root server will say, hey, yes. Right? So of course, the root server should not be compromised. Okay, everyone should know this because this doesn't change a lot. Then you kind of always catch that and get those public key early on. Then unless you are really lucky, right? So when a TTL and then you also get the public key record back. Okay. Otherwise, most of the time you will not. People may hold the right public key and you see a wrongly signed message. It will not take you your IP address to redirect. Okay? So this is a way that you can make sure there's some trust of the DNS server response. Okay. And so there are actually some service providers like VeriSign. So actually, they have another record called wildcard. Right? If you go to somewhere.com, but it actually there's no such record. Usually, let's say in your web browser, it should return you 404 error. But they have this record, catch all the records and point to another website by their company. Okay, and then they send a lot of advertisements. So if you go to somewhere that doesn't exist, instead of getting 404 error, it returns you some other machine address where you will go there and see a bunch of advertisements. Okay? So this is not controversial. Right? So this is like the service provider is running the DNS hijacking, okay, and it's abusing of trust by the side, right? So then the site was down, and there's lawsuits also. And there are a lot of other issues with DNS, right? Like the caching, when and how long, right? And how much to cache. And these are like the other uses of DNS, right? Like for content delivery, right? And how to do the load balancing, right? And if you are the mobile user, so you are driving to different states, how do you switch the DNS server and keep the connection? Right? And there's also like a security issues, how to tackle the botnet, DDoS. Right? So, and there's also a lot of political issues. Right? So how to avoid like how to, you know, like you can occupy some of the domain names, right? This is quite common. How to these issues, like, oh, you can occupy something like if you have like a bankofamerica.com, right? So you can have .c0 or something. Right? So Bank of America can be using some typo, right? Because there may not be the top level C0, right? But you can use some typo to occupy some similar domain names, and then use that to like as a fake address for some malicious use, right? So so how to address these things? Okay, there's a lot of other topics which we will not be able to cover. But you should be aware of them. Okay. All right, so any questions regarding this slide? I'm not sure, maybe I haven't put this slide on canvas. I will make sure it's on the canvas, and I will make sure, you know, the quiz is released today, okay? You will have a little bit more than 1 week for that, but, you know, because it's auto-graded, so you will, but try to get it done before the final exam. Okay, next week will be the last week. We will have the final exam go through after 2 more topics. Right. I see a question. So the exam will be Thursday and Friday, okay, of the week after, right? And then you can choose any 2-hour time slots to finish. So we will have 40 to 50 multiple choice questions, okay? And so because it's scheduled to be Friday originally, but there's a time conflict with commencement, right? So we make it flexible. Okay, it will be timed. You can do it anytime within these 2 days, but you know, once you start, it will be just 2 hours. Okay, and it will be multiple choice because we don't have time to finish all the grading if we want to finalize everything by the Monday after, as requested by UAB. Okay, so we will take all multiple choice. But we'll go through what you need to pay attention, right, in the last class, which was next Friday. So no worry. Any other questions? Yeah, so it's like a quiz, but it's time, okay? Because if you know, because we want to make it a little bit more flexible. So original time is not viable for many students because they cannot. Any other questions? Okay, if not, let's go back to last time. So last time we talked about you know, the problem with like synchronization of TCP. Okay, so we go back to the transport layer. Right? DNS is the application. Okay? And then if you are synchronized, and this part you are not using the throughput, but here you synchronize, everyone drops the flow. Right? So then, and when you get to the full bandwidth, get to where congestion happens, there will be long delay. This is what we talked about last time. And we talked about the RAD solution, right? So the random early detection. Okay, so this is actually you will probably discuss some packets before even the packet the queue is fully piled out. Okay, this is the probability decided as a function of the average queue length. Okay, so let's take a look at so this is average queue length instead of there's a smoothing over time, right? Because there will be some transient congestion, and you don't want to be overreact to that. Okay? So here's what is happening, right? So if your queue size, let's say this is total queue length, okay? And if your queue size is really empty, right? So then there's no need to drop any packets, okay? But when the queue size start to high up to some max value, you will random job some packets. Okay, and when it's getting very close, right, so you will drop packets with very high probability. It seems that we should connect these smoothly, right? But actually, we have the drop rate was relatively low until you get a max a lot. Okay, so this is one solution that you will drop early before you get to the go to max allowed queue. Right? You will start drop some packets when you get to min, and it increases as your queue becomes more occupied. Okay, so here are the red operations. If you are less than min, you always include packets. Okay? If you are larger, you always drop. Okay? But if you're in between, you include with some probability, which is between 0 and 1. Actually, the maximum is less than 1. Okay? And because the time is up, so I will continue, finish this slide next on Monday. Okay. Let me see, I have 4 more questions that I need to address in the. Oh, we don't have lab today. Okay, so because we have the final project, we want to give you, I mean, the optional project, we want to give you enough time to work on that. And the midterm final would also be from review slide. Yeah, so the final, we will have a review slides. Okay, everything in the final should be in the review slides. Otherwise, it, you know, because we covered a lot of things. Okay, the final originally. It should be in the form of like you have some question and answer and not fully auto-graded, right? So like do some calculation, Dijkstra algorithm, etc. Right? But we decided to make all these multiple choice. But you still need to do those calculation on your like scratch paper, right? And just when you have the answer, it will be one of the A, B, C, D, right? And you choose the right one, okay? Because we want to make the grading faster. And yeah, the review slide will be uploaded next week. Okay, so and next Friday we will go through the slide, and you will have another week to until the Thursday of the other, because Thursday is Friday of the week after. You can take it now. Okay. It should be enough time. Okay, so that's all for this class. Any questions? If not, be sure to check out the DNS and the quiz. Okay, do it early. Thank you, and we'll see you next Monday.